Welcome to the presentation of our paper titled Improving Trust Estimation in Human-Robot Collaboration, Using Beta Reputation at Fine-Grained Timescales. Let's start by defining the problem. In human-robot collaboration, a key challenge is how the robot adapts and adjusts its behavior based on changes in the human coworker's trust. For example, an intelligent robot collaborates with a human coworker by transporting a tile from the start position to the target position while avoiding obstacles. During this process, the human's trust in the robot may change as the robot performs the task. However, the robot does not know the level of trust the human coworker has at each step of the task. Capturing trust dynamics at fine-grained timescales is crucial, because it could enable the robot to adjust its behavior immediately, rather than waiting until the task is finished. To address this problem, we propose a four-stage framework for the granular estimation of human trust. In the first stage, the human coworker physically demonstrates the task to the robot, showing what is expected for effective collaboration. In the second stage, the dataset of human demonstrations is used to train a robot decision-making policy through behavior cloning and to learn an underlying reward function using maximum entropy optimization. After stage 2, the optimized decision-making policy and reward function parameters remain unchanged. As a case study, an intelligent robot learns a decision-making policy from human demonstrations for transporting a tile to a target position. After each collaboration task, the human coworker self-reports their trust using a 7-point Likert scale. We use percentages to interpret the labels of human trust numerically. In the third stage, the robot iteratively learns to estimate the human coworker's trust. In each iteration, the human coworker randomly sets a starting position, and the robot performs the task of bringing a tile to the target location using the optimized decision-making policy. After the robot completes the task, the human coworker self-reports their trust. In each iteration, these trust measurements are used to update the beta distribution parameters through maximum likelihood estimation. We use beta reputation to probabilistically estimate human trust at fine-grained timescales. It is based on a beta probability distribution defined by the parameters alpha and beta. Increasing alpha shifts the trust distribution to the right, while increasing beta shifts it to the left. Our contribution mathematically enables the preservation of a discounted history of trust estimations and allows the use of continuous reward values at fine-grained timescales. The final fourth stage is where we verify our proposal. Again, the human coworker sets a random starting position and observes the robot's task execution. While the robot performs the task, it can also estimate the human coworker's trust in it at each time step. This is achieved by assigning a continuous reward value at each time step and dynamically using these rewards to estimate human trust at more fine-grained timescales. It is important to note that human trust estimations are history-dependent, while the reward function is independent of the history of interactions. Finally, we analyze the comparative experimental results. From now on, while the robot performs the task, it can estimate human trust at each time step, whereas the human coworker can only provide a trust measurement at the end of the task. By continuously estimating trust during the task rather than only at its conclusion, the robot could, in the future, immediately adapt its behavior by deliberately acting to either enhance or reduce trust, addressing the pitfalls of overtrust or undertrust. By comparing the proposed granular estimation of trust model with a binary performance-based trust model, we demonstrate that our model estimates human trust at each time step of the task, providing estimations at more fine-grained timescales. In contrast, the binary performance-based model fails to account for trust dynamics throughout the task. Finally, note that with the proposed framework in this paper, we eliminate the need for the human coworker to assess whether the task performance was successful. As a result, the human coworker only needs to self-report trust without evaluating the robot's performance. Thank you for your time and attention. The source code for the implementations in this paper is publicly available.